Well, it looks like we can start. Welcome back, everyone. So we're about to close out week 5, so that means we're 1/3 of the way of all the instructional weeks completed. Congratulations, we're getting through it. We just have to do everything we've done to date 2 more times, essentially, and that's the whole semester minus the finals week. But any questions at all, folks, to start us out? Okay, well, for the announcements today, I did post a couple extra documents. There is a Calculus 3 application, as well as an extra example, 1 point from section 1.8. We will take a look at this one after we finish the 1.8 notes. And for the Calculus 3 application, I try not to post too many of these because this is not a prerequisite to this class at all, Calculus 3. But if there's ever a direct question in class related to this content, I'll usually kind of address it in this way by showing a particular application. So if you're curious what's going on with this one, and I think if you are taking Calculus 3, there might be some content that you're not quite into just yet called the Jacobian matrix. So if you have taken Calculus 3, you'd be familiar with that object. But the idea is, we said that this transformation here is a linear one. And we have pretty much proved it. We'll find out by once we exhibited the standard matrix A of the transformation T. We could break linearity in a big way just by going x1. That's one way to break it. Turns out we can break it again just by going something like this, a 4. That's enough to lose linearity. But having this, an x1 here, multiplying, let me get the subscripts right, is somehow a bigger departure. This is now a nonlinear function. If you ever had to work with a function like that, that's what this application here is all about. It's kind of the same thing, except I put xy in the second position, x squared in the third position. Linearity fails in a big way, so there's difficulty solving equations. Comment about how ordinary differential equations may be even worse or impossible to solve exactly. If you're curious of what the approach then is for linearization, it's all of this stuff right here. The calculus 1 analogy is, this is like finding the tangent line equation. Here, the linear transformation is this right here. We just multiply it by the variables x minus 1, y minus 1. When we put in this part, f of 1, 2, it's now called an affine transformation. So this actually breaks linearity in our strict sense from this definition down here. It's close to linear when we put in this function, but now L of xy is, in a certain sense, the best local approximation to the nonlinear function up here. So if we had to do anything algebraically scary with this or worse, we can get some great approximations using this approach. Well, that was my big application there from Calculus 3. Nothing really serious, more just a direct math application. What we'll do next is finish off the 1.8 notes, possibly move into 1.9. I don't want to make too much headway in here. We don't want to rush through the notes. But any last questions at all, folks, before we get started? Okay, so here's where we left off. We're taking a first look into the definition of linearity. The notes are more about learning how to work with the transformations as well as navigating through this definition. So a transformation T being linear, we mentioned is a set of operation preserving features of the function. If you have a scalar multiplication inside the function, you can use the transformation T and operate on the output there, or you can just take the transformation of U, the transformation of V, and add the outputs in the codomain space. Likewise, scalar multiplication can be done in the domain space, or out here in the codomain. T of U is now in the codomain, say Rm. So those are pretty interesting properties. We'll see a lot of interesting ideas that go along with them. First thing we'll do is just practice dealing with some of these elements. Example 2 is still more about learning all the parts, quirks, and features about transformations from these kinds of larger domain and codomain spaces. So we have a transformation, T of x, defined by just a matrix times a vector. The standard matrix A, which we'll call later on, is this 2 by 3 matrix. we want to know what is the domain and what is the codomain. And this is honestly a pretty confusing question. It's a standard one that could come up on exam 2. The answer is not things like 2 or 3 on any one of these. The answer is going to be something that looks like this. We just have to fill in the numbers. One way to think about this, though, is just rewrite the function. If t of x equals ax, well, throw in the matrix A. It's 1, -4, 2, -5, 3, -7. That gives us a 2 by 3 matrix. And the only way this matrix multiplication is going to be valid is if we take a 3 by 1 column vector. So we'll have to have an x1, x2, x3 in the picture. Let me kind of make that look more like a subscript. So this x1, x2, x3 is the x that goes here. It's the x that goes inside the function. So it came from that spot right there. We're always going from domain. The arrow says pointing into the codomain. So just by rewriting the function in this form, we can tell right away the domain has to be R3. Does that make sense to folks on getting this response here for domain? Okay, other thing that might be highlight worthy is that 3 there and that 3 there was telling us what the domain was. And now if we were to do this matrix multiplication, maybe we had constant values or we just want to multiply it out with x1, x2, x3. We also know the size of the resulting vector. It would look like this. I'll leave it unfilled in, just a little dot here to say some algebraic expression and some other one. The reason it's going to be 2 by 1 is it comes from these outer dimensions. So really, this is just kind of a review of a matrix times a vector concept. But this 2 by 1 vector is in the codomain space Rm. So we have, for the codomain down here, codomain of t is R2. So that tells us what the picture looks like for domain and codomain if the function is defined in this way. So you might say slightly differently, if you're answering both A and B in the same time, you would say T maps from R3 to R2. And notice the kind of reversal of dimensions. If T of x equals A times x, and A is of size 2 by 3 because it has 2 rows and 3 columns, that 2 goes over here, the arrows crisscross. The 2 is the codomain dimension space. The 3 is the dimension of the domain space. So flip them around and you've got domain to range. Well, codomain is the better word there, not necessarily range, although it would look like it on this one. Does that make sense to folks on just looking at this bit of domain codomain surgery on the function? Okay, next thing we're going to do is a verification problem. We're just writing down a really strong argument. You could call it a proof, but nothing too heavy on this one. We're just following through what the definition is saying and show once and for all, if the mapping is defined as a matrix times a column vector, it's linear. Didn't have to be necessarily this matrix. Any size matrix would have done the job for us. So let's work this out. We have to show 2 parts. Really, part C is just getting used to these definitions. And the big part of these definitions is where it says for all. In the domain, we have to pick arbitrary vectors. We can't pick vectors like 1, 0, and 0, 1 and show it works for those. We have to show it works for any vector whatsoever. So we can work abstractly by just simply saying, let UV be in, it had to come out of the domain of T, so it has to be in, let me fix my color, one moment. It has to be in R3. And that makes sense because the mapping is going to just multiply those vectors U and V. It has to be of size 3 by 1. We never said what the vectors are. They are completely arbitrary. We just know they each have 3 entries. This could be the 0 vector or otherwise, and so on for V. Now we could work part I But I think it's sometimes slick to write this down as one compact argument by doing the same with the scalar c. C could be 0, pi, 20, a million, any scalar whatsoever. And same idea, we have to pick an arbitrary scalar. Let's see, b, you could just say any scalar, any real number. I'll say it briefly this way. Let C be an R. So we'll do both parts one, parts two. We have all the objects that are going to move around. We have an arbitrary scalar C and arbitrary vectors U and V. So let's try out part one. We need to show that T at U plus V, do some algebra where the red dot is, a long chain of equalities using transitivity of equality, eventually outputs T at U plus T at V. So if we can write down a bunch of equalities that gets to where that red dot is, our job is done. So we're stuck here, T at U plus V. And all we know about T at U plus V is that T of X equals AX. This whole entire U plus V is like the X. So it goes into the input position to the function. So the output would be A times whatever the new input variable is. Now it's U plus V. So far we're just using ordinary function notation. And now we have a matrix multiplying vector addition, but that's where this stuff comes into play. This is the same theorem above up in the notes, just a screenshot. If you have a matrix A, any matrix A, and you have a vector addition in the middle, you can distribute as a punchline to this property. So this turns into A times U plus A times V. And we're totally done with that property now. Let's bring it up so we can see some properties all at once. So we used the definition of the mapping going this way to get started, but now we're going this way, we're reversing it. We have a matrix times a vector here, another matrix times a vector there, and if we reverse the directionality, we get the mapping T back. So right where this is T of the vector U. Then plus, right where we say A times V, well, that's just A times X. V and X are taking the same role. So over here, we'll put T of V. And that's precisely what we want to show. T at U plus V equals T at U plus T at V. And so part one is done. On our way, we just have to show one more part. Let me make this all one big kind of a paragraph. I'll say since, and then long string of equalities to link up T at U plus V equals T at U plus T of V. And since, now we just want to show the second part right here. Same idea, we're going to take T at C times U. That C times U is playing the role of X right here. We're now using the mapping going left to right. So that says, take A times whatever the input is, no matter how ugly, how strange. This time it's just scalar multiplication. This results in A times CU. So the rescaled vector U. At this point, you probably have a good idea what we're doing next. We go to theorem 1.4, and we use this property. Scalar multiplication has a type of commutativity. The C can commute out here, and you could just take A times the vector U and scale the result of matrix multiplication there. So by that property, this could be rewritten as C times A times U. We're allowed to associate this way as well to emphasize this part. And that's helpful for us because now, just like in the last part, we're going from A times X, X just happens to be U, and rewriting it with the mapping T. This turns into T times U. But that's specifically what we want to show right here. It just took us more than one equality to get there. Took 3 on that one. And so that's the second part of linearity. This is all one big sentence. It said verify T is linear. Really, those are the two core parts we have to show, but it really flows as a sentence. Since this property held and this property held, T is linear. Any questions at all, folks, navigating through this kind of problem here? Yeah, absolutely. Thanks for spotting that. I think I got too excited on the conclusion there. This C is still there. Thanks for spotting it. Has to be there for the actual direct property too. Other questions at the moment? Let me fix those equalities to fit them in well. Okay, so this is a check of linearity, but like we mentioned, the matrix A didn't even enter the picture. That's what's kind of interesting about this. You could have worked this problem in the same kind of way by writing U equals U1, U2, U3, V equals a column vector, V1, V2, V3, and really painstakingly directly verify these two properties. However, through this theorem, we just knew whatever the matrix was, we already had this distributive property. We already had this kind of commutativity property. So our work was done the moment we used it. It's concerning deleting a theorem, but recall it's also up here. That was just a quick screenshot. Well, this is just a way to think about what we mean by linear. We'll do a couple more problems working with linear on these notes. A couple more problems just practicing dealing with transformations T. Any questions so far? Okay, so weird objects of study. Really, we're just looking at functions like in a college algebra, pre-calculus 1 sense. It just so happens our domain and codomain are vector spaces. Vectors, column vectors with n entries or m entries and so on. And this theorem is kind of the wrap up of what we were looking at with that last problem. Connecting the theorem from section 1.4 with the definition of linearity tells us the transformation T is defined from Rn into Rm by T of x equals Ax, where A is an m by n matrix, then it is a linear transformation. That's big, so let's just highlight it. The transformation T is automatically linear the moment you exhibit it, that matrix A. That means sometimes these are really, really fast concept questions. This question here says, let the transformation that goes from R2 to R3 be defined by T of x equals Ax. Notice how funny that looks. There's no parentheses there. Actually kind of bothers me, but in a certain sense that is appropriate. Sometimes these transformations are written that way. But I think I would have often usually written it this way if it was like an exam question. I'd prefer just emphasizing the fact it's a function with legitimate function notation. So T of x equals Ax. A is the matrix that goes like that. Notice once again that this is a 3 by 2 matrix, and the 3 by 2 is reversed. The domain is R2, the codomain is R3. So there's always a switch of the dimension and domain into codomain. We're asked, is T linear, and briefly explain. But if we cite the theorem above, this is all we have to say. We don't need to do this every single time we have a transformation defined that way. That'd start to feel extremely redundant. So we'll just cite the theorem. Since T of x equals Ax, where A is a 3 by 2 matrix, T is linear. And that's awesome. That's about the fastest problem ever. It's also a tricky one because, again, it was all about knowing that this automatically gives us a linear transformation, knowing that this theorem is working for us in the background. Second part is, well, just working with that transformation T. It doesn't do anything with the linearity specifically, but we'll see some problems where we do use linearity directly. It asks, for what x in R2 does the equation T of x equal 103 hold? Really, it's kind of just a review problem, working with row reduction, solving matrix equations, T of x equals 103 directly implies well, T of x is defined by AX, so it means AX equals 103. That means we can just take this entire matrix equation that we see right here, go into an augmented matrix, and just start row reduction. So here's what it would look like. The augmented matrix is going to be A augmented with 103. That's probably not the best notation. Let me find a better way to write that in. Let me go 0, 5, negative 1, 1, 5, 0. And I'll just indicate that that's the matrix A in this kind of way, augmented with 103. So that's the right-hand side of the equation here. And maybe another punchline with this whole problem is there's a reminder now that you can write equations in now 4 different ways. You can write it as a system of linear equations, just line by line, equation 1, 2, 3. That's what we did in section 1.1. Section 1.3, we learned we could write it as a vector equation. So that's a second way. Section 1.4 was the matrix equation. And now this is just an equation using the transformation, the 4th different way to represent really the same information. And the methods to solving this would be the same as well. Lots of different things you could do. Maybe take row 2, divide it by 5, and promote it to row 1. We'll get 1, 1, 0. You might have done something different. Maybe you made row 3, row 1. I'll make the row 3 the row 2, negative 1, 0, 3. And I guess now row 1 can be row 3, 0, 1, 1. So I scrambled the rows and also divide row 2 by 5. Seems like a good way to go. We can start directly adding row 1 to row 2. Add row 1 to row 2 to get 0, 1, 3. And we have 0, 1, 1. And so far, the other reminder about this is it's asking for what x in R2. It's not asking if it's consistent or inconsistent. This is looking for a direct solution. However, if it's looking for a direct solution, you would want row reduced echelon form, right? But if you're looking ahead to the next step, it looks inconsistent. So let's just go for echelon form and show that's inconsistent right there. Reason it's inconsistent is because it looks like we're going to get a pivot in the rightmost column on this one. So it's 1, 1, 0, 0, 1, 3. Multiply row 2 by negative 1, add to row 3 to get 0, 0, negative 2. And our job is done at this point. It said, for what x in R2 does this equation hold? The answer to that would be no such x. This system is inconsistent. So T of x equals 103 is a lie. You might write it this way. It's not equal to 103 or all x in R2. Or you might have just said no solution, but emphasizing the mapping, this is a different way to say it. Well, any questions with this one, folks? Kind of like a relaxing old problem from back in the day. Okay, so far, we haven't done a whole lot with our linear transformations. But this one's a special problem. It says assume T mapping R2 to R2. Sometimes these are called linear operators, where the codomain and the domain are the same space. It's kind of a cool word, so let's say it here. An operator. What's also linear. We're told it's a linear transformation, and it maps x to 4, 1. It's kind of a mysterious statement there. It maps y to negative 1, 0. We have to unpack the language as well when we do these kind of problems. When they say mapping, they're saying apply the function mapping t, or apply the transformation t. So in other words, this whole statement here with a bracket in orange is just saying t of x is 4, 1. Maps y to negative 1, 0, same thing. That's just saying t of y equals negative 1, 0. You might also ask, why not just say it this way? This in some way is a little bit more clear. It's literally saying what the function is doing, that you're using the function, and what the output is. Well, reason people write these things this way is stylistic choices. Sometimes it just looks better on typesetting. And our author does this a lot because he wants to just quiz us on the definitions and the vocabulary, the terminology. So concepts like these, which were really familiar, sometimes get a little bit mystified in the actual homework exercises in this kind of way. It's our job to unpack what it means. And this helps, just write down something on the notes. What we're actually doing is evaluating t at 2x plus 5y. So let's do that evaluation. But as we stare at this, notice the difficulty here. Our training in algebra says do order of operations. In other words, do the vector addition, scalar multiplications inside here, then apply the mapping. But we can't do that. We were never told what x actually is. We were never told what y actually is. We don't know much about this. So in a certain sense, we're stuck. Sure, we've used this information by showing what t of x equals, what t of y equals. You know, one piece of information we didn't use, not yet, is this. The fact that it's linear means we have extra algebraic properties available to us. So that's this part of the notes that was hidden briefly. Because t is linear, we can take advantage of properties 1 and 2. So that's what we'll do next. Any questions at the moment with the problem so far? Okay, here's one way to apply this property. So it says t at u plus v equals t at u plus t of v for all vectors uv in the domain of t. Well, it looks funny, but yeah, that's a vector. It's just been scaled by 2. It qualifies as a u. This qualifies as a v, even though it's being scaled by 5. Nothing prevents us. They are still vectors in R2. So scaling doesn't matter here. You can still apply property 1. And this turns into t at 2x. Let me actually undo that. We'll use another highlighting in a moment. Plus t at 5y. So this is by property 1. And you probably can predict what we're going to do next. Property 2 is in the picture here. A little bit easier to actually see algebraically. The scalar c's are going to be the 2's and the 5's. That says, sure, we still can't scale 2 times x because we don't know what the vector x is, but we can just pull the 2 out. We can use this property right here. So this turns into 2 times t of x plus 5 times t of y. And this is where the information in the problem is finally relevant. We know what t of x is, and we know what t of y is. At this point, we can put in those outputs. So in other words, we can never do this work in the domain. We had to do all of our work in the codomain after mapping x and y by t. So this becomes 2 times t of x is 4, 1, plus 5 times t at y is negative 1, 0. Then it just becomes a linear combination problem. We're essentially done at this stage. And you can kind of see the shortcut already. If you're doing t at 2x plus 5y, you just take 2 times the output plus 5 times the other output. I encourage you to take these steps right here because we're trying to form that mental glue of how do you actually use the linear transformation. So you won't be docked points on a homework problem if you didn't show that, but it's good practice. It'll get us prepared for when we do it in an exam setting. So now it's a relaxing problem. Scale that vector 4, 1 by 2. It becomes 8, 2. Scale the other vector by 5. It's now negative 5, 0. And so the output to 2x plus 5y is just 3, 2. All we needed was those two parts of linearity. So in a certain sense, the big part of the problem was right here. And a good problem-solving strategy is if you ever read one of these questions in the homework, you're not sure what to do, look for something in the statement of the problem that you just haven't used yet. Seeing linear transformation meant we could just drop onto this definition and work through the problem. Well, any questions, folks, with this kind of a faster one? Okay, let's maybe screenshot this thing or copy it. I want another version of it down here. We'll see why later on. Example 5 is different from before. It's more information about how we sometimes write down these transformations, a little bit more about how we work with the transformations. But maybe the big part of this example 5, and the reason I like it, is that's a good review problem on parametric vector form for solution sets. So we have a rather large matrix on this one. I think there's a couple large ones in the homework as well, so I was motivated to bring a bigger one to class. It says find all x in R4 that are mapped into the 0 vector. This tells us right away what we're dealing with is a homogeneous system. So mapped into the 0 vector by the transformation, and that looks really weird, right? Some of you might have seen this kind of notation before. What this is saying is x and that particular arrow in that exact form, change the arrow and you might change the meaning. X arrow ax means x is mapped to ax. So that's all the arrow is really saying. It's a literal mapped to. That means there's a transformation t in the background here, but for reasons that only the author could explain, he decided to not write in t. He just wrote it this way: x maps to ax. It's a way of indicating a function. I think it's a weird way to do it personally. It's vague, but it's common enough that it's worth bringing into the notes. Occasionally our author writes theorems in this way, like the invertible matrix theorem that's coming up. If you don't like it, if you're not a big fan, you could always do this. It's up to you to decide what notation you want to really work with, and nobody's going to stop you if you say T is going to map R. Let's see, there are 4 rows and 4 columns. So take the number of columns, that's going to be the domain 4. It's going to map into the codomain space, number of rows, which is also 4, is given by or defined by T of x equals ax. Same exact information here. Perhaps that's why people like it. It's really, really compact. It's a terse statement. I like this a little bit better personally because it's telling me every single bit I need to know in very, very plain terms. The transformation is just T of x equals ax. Any questions at all, folks, about the terminology or the notation? Okay, so, well, now we have to solve something. Find all x in R4 that are mapped into the 0 vector. That just means solve T of x set equal to the 0 vector. This is the 0 vector in R4. But T of x is nothing but a times x. So this would be a times x set equal to the 0 vector. And now it's really just a problem like what we've done in section 1.5. This has, we're going immediately to the augmented matrix. It's kind of a big one, so let's put this in carefully. And the rows don't look like they're the most convenient format. But let me put them in as they are right now. 3, 2, 10, negative 6. Then we're augmenting with the 0 vector, so 0. 1, 0, 2, negative 4. Then a 0, 0, 1, 2, 3. 0, and 1, 4, 10, 8, 0. So that's our system to solve, kind of a larger one. We have variables x1, x2, x3, and x4. Now we can start. And there's a lot of choices you might make on this one. I think for me personally, I like row 4 being row 1, so I'm going to move that to the very top. 1, 4, 10, 8, 0. And this looks like a, you know what? I would put this one in row 2. What I'm kind of trying to do is arrange it as close to an echelon form already, just by interchanging these rows. So that looks like a pretty good row 2. It'd be 0, 1, 2, 3, 0. This one, it's easy to eliminate that 1 there. Then I'll have a 0 and then a non-zero entry right here, which would be a non-zero entry at this location. That means row 2 is probably a good row 3. 1, 0, 2, negative 4, 0. This isn't the only way to do it, but sometimes taking a little extra time and trying to devise the least amount of work is a big help on these. And this looks like a good rule 4. Not too much to do with this, except to eliminate entries. 3, 2, 10, negative 6, 0. So automatically we have a pivot here. We're eliminating these two entries below. So row reduction really starts to begin in earnest on this step. Let's copy in rows 1 and 2. 1, 4, 10, 8, 0. 0, that's a 0. 1, 2, 3, 0. Multiply row 1 by negative 1, add to row 3, and we'll get 0. Negative 4, that's a negative 10 plus 2, so a negative 8. This is negative 8 minus 4, so negative 12, and 0. Good idea to double check with all these numbers. Okay, I think we're so far so good. Now to eliminate the 3, we're multiplying row 1 by negative 3, adding to the row below. So we'll get 0 here, then negative 12 plus 2, negative 10, negative 30 plus 10, negative 20, then negative 24 minus 6, negative 30, and a 0. This is just about where we would want it. And notice something nice about the rows all of a sudden, right at this step. Row 2 is just negative 4. Well, let me say this again. Row 3, that's where the red dot is, it's just negative 4 row 1. Row 4 is just negative 10. Oh, I said it wrong again. Let me start over. Row 3 is negative 4 times row 2. And row 4 is negative 10 times row 2. I think I got it on the third try there. That means these are all just zeros officially. Let's work it out carefully just to make sure we did see an optical illusion on accident with the row reduction. And really, we're going to pivot off this entry right here. So let's also just copy in row 2 to start. 0, 1, 2, 3, 0. Sensing this is the last step on the reduction, so let's put in the fact it's augmented. I can't change column 1 whatsoever, nor the 5th augmented column. So we can put in the entries that will never change. Now take negative 4 times row 2, add to row 1. We'll get 0. Negative 8 plus 10, so positive 2. Negative 12 plus 8, so minus 4. Look all right so far? Okay, next operation is 4 times this row, add to the row below, but that would be 4 minus 4 for a 0, 8 minus 8 for a 0, 12 minus 12 for a 0. So this is where we're kind of coasting at this stage. Same sort of thing, take 10 times row 2, add to row 4. That's 10 minus 10 for 0, 20 minus 20 for 0, and 30 minus 30 for 0. So all this stuff is zeroed out, kind of lovely in a way. We have variables x1, x2, x3, x4 in our system. And now this is just a review of getting it into parametric vector form at this step. Basic variables are x1, x2, so we want to solve for those in terms of the free variables, which are x3, x4. These ones take now a really special role in parametric vector form. Reading out row 1, it's x1 plus 2x2 minus 4x4, or let me say it again, it's x1 plus 2x3 minus 4x4 equals 0. So we can solve that equation directly right here. X1 is now directly equal to negative 2x3 plus 4x4. Same trick on this one. This is an equation set equal to 0, but we're imagining subtracting 2x3, subtracting 3x4. So this one reads out as x2 equals negative 2x3 minus 3x4. Free variables are x3 and x4, so we might just write x3 equals x3, x4 equals x4. So here's where the free variables land. Now we're just about ready to write down all vectors mapped into the 0 vector by this transformation here, or indicated by t down here, same exact algebra. The punchline is t of x equals a 0 vector implies x, which is a column vector of 4 entries, x1, x2, x3, x4, is equal to a linear combination. The scalars are the free variables. We'll put in x3 here. Multiplies the constant vector. And the coefficients go negative 2, then 1 in this position, and 0. Then go plus x4. That was weird. Half of it was blue. Plus x4. Coefficients for x4 go 4, negative 3, 0, and then 1. And we can say, if we want to be specific, where x3, x4 are in R. And we've done it, folks. That's our parametric vector form here. Any questions at all, folks, getting to that stage there? Okay, pretty much, again, it's a review technique, but we've said a lot how this just keeps on coming back in really big ways in the later chapters, particularly in chapters 4 and 5 together. And just a preview on what's coming up not too long is 2 concepts. We might say KERT, the kernel of T, or in a different way, if we were deciding to not emphasize the transformation T, but we want to emphasize the matrix A, we might call this null A. This is referred to as the null space of A, and all of this is just the span of these 2 constant vectors here and here. The punchline with parametric vector form, like we've mentioned, are those constant vectors. That's why we undo the vector addition. That's why we separate out the scalar multiplication. The null space is negative 2, negative 1, 1, 0, comma, 4, negative 3, 0, 1. So if you can get down to this statement in orange, it means you can compute things like eigenvectors in chapter 5. It's all pretty much this same exact technique. The actual instructions for this problem would end right here. If you wrote null space A as the span of this, you're saying literally the same thing. This is just a preview topic coming up soon. So we made a lot out of this problem just because there's really a lot going on anytime you're doing parametric vector form. Any questions whatsoever with the conclusions here? Okay, let's take a look into what else we're getting into on this. Next problem is just another one looks like dealing with the linearity property of a transformation. We have x is x1, x2, v1 is -3, 5, v2 is 7, -2. T maps R2 to R2, so this is another linear operator. The codomain and domain is the same. It's a linear transformation that maps x into x1, v1 plus x2, v2 by the matrix A such that T of x equals AX for each x. This technique is important to us as well because knowing how to do example 6 is just another way to prove this is actually true, that the transformation T is in fact linear. If we can't write down the standard matrix A whatsoever, then we don't have linearity. Or maybe something else is going on. If this is a different vector space, not a list of entries, that might be one reason we can't write down the standard matrix A, even when it is linear. This one's just a kind of review of other algebraic review properties, matrix multiplication and linear combinations. When it says a transformation maps X, we're talking about T of X. It maps it into X1, V1 plus X2, V2. And this is just a linear combination of vectors. The important concept about this is any linear combination of vectors is just another way to represent matrix multiplication. Here's how it could be rewritten. This is the same thing as V1, V2 multiplying X1, X2. Let's see if that multiplication is legitimate by filling in V1, V2. So V1 is the column vector -3, 5. V2 is the column vector 7, -2. This is multiplying the column vector x1, x2. And yeah, if this is size 2 by 2 and this is 2 by 1, this multiplication works. What we were trying to do is find the matrix A. And there it is, such that T of x equals AX. So we can say the problem is now complete. A equals -3, 5, 7, -2. So really, again, the punchline to this one is all you had to do to find that matrix A was drop -3, 5 here, take 7, -2, drop it here, and that actually did the job. There's a more general theorem all about this that we're going to take a look at into section 1.9, which has to do with a new concept called basis vectors, kind of a preview concept as well to chapter 4. Other additional comment is we refer to this as the standard matrix. Kind of butchered that word. Let me try again. A of T. Well, any questions, folks, with that quicker example 6 here? Okay, you might notice a lot of these things on the notes are kind of review topics. I mean, we redid parametric vector form. We redid finding an inconsistent system on the problem before that one, and some problems dealing with linearity. So we're jumping back to more linearity problems finally on last two examples of the notes. Example 7, showing a transformation is not linear. So we're showing when linearity fails. We did a lot of problems showing things are linear. So it's just as important to turn it all around. And example 8, slightly harder one, will show that this one is not linear as well. Reason example 7 is a kind of a nice one is there's a nice theorem that you can use. The little border there. It turns out if you have an honest to goodness linear transformation, linear transformations preserve the zero vector. The zero vector in the domain space will always map to the zero vector in the codomain space. So that's a really nice formula right there. Let's test it out to just give a quick argument, just to study the definition of linearity once more. The way we can verify that this theorem is valid is we can say, let U be in Rn. So I took a vector out of the domain space Rn. let C be an R. So I'm looking at this part of the definition. I want to grab an arbitrary scalar, so it looks like we're dealing with this part. T at C times U equals C of T times U. And you know what, let's be specific. Let C be an R. Take C equals 0. This works for all scalar C, and for this particular theorem, I want the 0 scalar, so C is 0 on this. On one hand, we know that T at C times U is equal to C times T at U. That's just because we're told the transformation is linear, so we just literally copied part 2 of the definition. But part 2 works for all scalar C, and we took C equals 0, then this implies T at 0 scaling the vector U is equal to 0 scaling the vector T of U, whatever this output is in the codomain. The facts we know about scaling any vector by 0 is it turns into the 0 vector. So now that's 0 as a vector, whereas by the red dot, it was 0 as a scalar in the real number system. And same exact principle. It doesn't matter where T maps any longer. If you scale it by the 0 vector, it's now a 0 vector in Rm, the codomain space. That's precisely the theorem. Because of linearity, you could have picked any C, and once you have that freedom, you get interesting properties like these. T always, if it's linear, maps the 0 vector back into the 0 vector. So that's kind of a cool property. And we'll apply it right away on example 7. Any questions about the property or the argument? Don't know why I scrolled so far down. Okay, let's put it to practice. Notation here is written more in like a calculus kind of way, but our author does this often actually in our textbook. I think we mentioned the comment, it was probably to save on vertical space. It made the book a little bit cheaper, like $1 maybe. So if you want to fix the notation, it's optional. You can rewrite it as T of X equals T of X1, X2, which is equal to, this one has 2 entries. So first entry at the red dot is 2x1 minus 3x2. I'd say the best way to do this is just to train your eyes to see it both ways. Oh, excuse me, 3 entries on this one, x1 plus 4. And then the third entry is 5x2. And let's just go ahead and apply this theorem. Since T, mapping the 0 vector, said differently, it's T at 0, 0, becomes, well, here's what we're doing. Everywhere we have an x1, that's this position, or an x2, that's this position, we're throwing in 0. Row 1 is 0. It's just 0 minus 0. Row 2 is 0 plus 4, which is 4. Row 3 is zeroed out. But this is not equal to the 0 vector in the codomain space, 0, 0, 0. In other words, this was violated, and this immediate not equals right here tells us T is not linear. All due to that not equals there. If T were linear, it would have satisfied this property. Well, any questions, folks, using that awesome theorem there? This theorem can save a lot of time, but you know there's a downfall to this theorem. It can be misapplied. A way to look at this again is, you could say more briefly that T is linear implies T of 0 maps to 0, but the converse is false. What we mean by the converse is if t at 0 equals 0, I can't change the logic and come over here and say t is linear, and that's pretty unfortunate. In other words, there's no double arrow on this one. The directionality of these arrows really does matter. So just because something maps to the zero vector does not prove linearity whatsoever. We might have to use this definition. That's what's going to be relevant on the next example 8. So let's take this definition with us. It says, show that the transformation t, defined in this new way, is not linear. First, if we were to check out t at the zero vector, we could have written it this way, t 0, 0, maintaining the sideways notation, just to see it a different way on this one. This would turn into, well, this will be 0 minus 0. Second entry is just 0. Because it equals 0, this gives us no information. That last theorem is only informative for us if it turns out it's not equal to 0. So even though the theorem is fantastic, the logic contained in it is really, really limited if we're facing example 8, and we're still trying to show it's not linear. So let's work this one out carefully. If something is linear, we have to work with these objects for all vectors u and v. Sometimes these are called universal quantifiers because we're talking about any vector u, any vector v whatsoever in the domain of t. And we have to work with all scalars c. That's if we're proving it's linear. However, if we're told something is nonlinear and we're told to show it, we're going to take their word, it's nonlinear. We're not trying to work with for alls anymore. We want a particular counterexample. So a counterexample is going to be a specific pair of vectors u and v, or a specific scalar c. So that's what we're trying to do this time. A counterexample is a specific vector slash scalar. I'll write it this way because you might try to do this by part I. You might try to do this by part 2. There's a great question in class about when things are not linear, can one of these fail one at a time? And it turns out that is true. But most of the examples that I've seen in the actual book, the one I brought to the notes, turns out it's more typical for them both to fail at once. And if that's the case, part 2 is probably a good starting point. It's just the simpler property to work with. I'll have a simple scalar, we have to pick it, and a simplest vector we can use. Not the zero vector, we've already tried that route, so we want something other than the zero vector. The big feature about this problem is x1 times x2 is what's causing nonlinearity. We just have to really show it by the definition. So I probably wouldn't want x1 nor x2 to be equal to 0. I want them to survive to show what breaks, in other words. At least that's my initial thought on that. Sometimes this takes a bit of creativity. So here's a counterexample that could work. Let u equal, this is the uncomfortable part. It's weird when you're doing a math problem and now you have infinitely many choices. Try to work simple. Maybe what could work here is, how about 1, 1? Maybe 1, 0 could work, or 0, 1 could work. But my thought is maybe not letting them zero out is a good try. If I don't get a counterexample here, that's okay. We'll just start over and try again. So we're really focusing on this part. I had to come up with the vector u. Now I have to come up with a scalar c. And let c equal, well, we don't want c to be the zero scalar either, because then that would be the zero vector on the inside, and we've already tried that out. Any volunteers for a choice of a scalar c? Weird, because we have lots of freedom here. Here's one. Oh, sorry, go ahead. Oh, sorry, I thought I was about to talk over someone. Yeah, that's a great thought. We know in algebra that negative signs mess things up, right? So let's try a negative sign, see what it could do right here to cause some problems. So c equals -1. I think that's a good choice to get started. And if this doesn't work, change something up. Maybe change this to positive, see if that fixes it. Maybe change this to maybe a 2, 3. Maybe unbalancing these is what was going to cause a counterexample. Who knows? We just have to try this out, see what happens. These are kind of tough problems. So if you get stuck on these, don't hesitate to email. I'm happy to help out with this kind of problem. So I think this should work as a counterexample. But here's the next phase. Step 1 was to pick your scalar and your vector. Step 2 is to look at both sides of that equation. So let's say here, on one hand, I'll look at the left side first. T at c times u is equal to t at, maybe before I get too far along, let's reformat this one as t at x equals t at x1, x2 equals 4x1 minus 2x2, x1 times x2. I'll visualize this one as an actual column vector. You don't have to. If you keep it as a row with comma separated, that's completely fine as well in your work. This is going to turn into t at -1 times 1, 1. So all I've done is filled in c, filled in the vector u. Let's do the scalar multiplication. This is t at -1, -1. So -1 is the x1 component going here. The other -1 is the x2 component going here. So nice substitution. This will become -4 plus 2. Once we drop in those negatives, deal with the double negation. This is -1 times -1, so it's a positive 1. So this becomes -2, positive 1. So double checking, that was a -4 minus 2 times -1, so -2, and then -1 times -1. So that's our left-hand side. And now our hope of hopes is that that equality right there is broken when we do the right-hand side. So let's say here down below, on one hand, we got that. And on the other hand, C, scaling T at U, is going to be, first we fill in the information. C is just -1, so this can be rewritten as -T. Mapping, here the vector U is 1, 1. So this will be negative times T at 1, 1 is just plugging ones where x1, x2 are. It's kind of nice having 1, 1s. We can't get mixed up on what goes where. This will just be a 4 minus a 2. So positive 2. This is 1 times 1, so positive 1. And looks concerning, except remember we're scaling the whole vector. This will turn into -2, -1. That's good because now T at C times U is -2, 1. C at T times U is -2, -1. We've broken the equality right here. We just have to write down our punchline. This shows T at CU is not equal to CT of U. And so T is not linear. We've broken linearity because the statement for linearity said it had to work for all scalars C and all vectors U. This is what we mean by the counterexample. It does not work for all vectors C, or let me say this again, does not work for all scalars C and all vectors U, because here's a pair of scalar vector where we literally broke the equality, and we see it right here on paper. Entries 2 are different. Looks like that negative was key because it's the negative times a negative property that's broken on this one, losing linearity. Other things could have worked. You could have done part I. Maybe U is 1, -1. Maybe V is -1, +1. See if that one works and see what happens. I think this is usually a good place to try. If I got too frustrated here, I'd probably change gears and try property one next. Well, any last questions at all, folks? Getting through this one? Okay, I have some other problems down below that, in my opinion, seem exciting, but this is only if we had extra time. We're a little bit behind on the course, so I think these are skip worthy thanks to that fire alarm. If you're curious about these kind of problems, don't hesitate to ask. I'm really happy to put down the solutions. Essentially, what these are each saying is, if you have a linear transformation and you have a set of vectors that spans the space, any one of those vectors mapping to zero, excuse me, if every one of those vectors maps to zero, T is the zero transformation. T is just literally setting everything to zero whatsoever if it maps everything that spans the space to zero itself. An even more interesting property is T being a linear transformation actually preserves a lot of stuff. If you have a linearly dependent set in Rn, it will map to a linearly dependent set in Rm. So it preserves linear dependence. Well, does not preserve linear independence. That's a little bit weird. Those are some additional properties, but I also wanted to show, just for the sake of variety, one more example along these lines. So example 1.8, the extra example, is kind of an unusual one because this is a problem where linearity fails in a strange way. One property works for this mapping, going from R2 to R2 again. Notice how convoluted it is. It's the cube root of x1 cubed plus x2 cubed. And then in the second component, just x1 minus x2. It turns out that it preserves c t at c times x equals c at tx. So this one's preserving part two. It actually works. You can prove it. That's what all this algebra here is about, if you like to track it through. However, the t at u plus v equals t at u plus t of v, the first property of linearity, it actually fails. This right here is a counterexample. If you take t at u plus v, you get to this result. But t at u plus t at v, work it through on the mapping carefully, and you get something different, 2, 0. So this one's unusual because it breaks property one, but property two holds. I thought these would be a lot easier to find, but these are actually pretty hard to come up with. And another comment is you can actually have this hold and this one fails, but that's an extremely hard counterexample. People have worked really hard to show this one. It's out there. If you're curious about it, let me know. I'll be happy to post the details. But it turns out it's some pretty heavy reading on that one. Well, this concludes our introductory topic on linearity. I don't think I have a lot of time to get too seriously far in section 1.9. I just want to point you in the directions we're going to go on this one. This one is going to be collecting properties about linear transformations. First thing we're going to look into is how to build the standard matrix through this theorem right here. You need certain key vectors. These EJs or EIs, E1 through EN, turn out to be an interesting key for coming up with the standard matrix of the transformation. These vectors are so important, they have interesting notations, and we'll later have interesting names we're going to label them. We'll call these the standard order basis vectors. So we're going to look into some interesting notation, talk about identity matrices in now a very firm way, show how to do a cool theorem that just assembles the standard matrix T using the columns of an identity matrix. Then talk about onto and one-to-one, and that seems like a weird thing to do, but this is a really big punchline about linear transformations. We really like linear transformations that are one-to-one and onto, so we'll collect some theorems. We'll say T is one-to-one if and only if T at x equals 0, that's the homogeneous equation, has only the trivial solution. That might ring some bells. Having only the trivial solution is linear independence, right? Linear independence is tied together with one-to-one. And having only the trivial solution, this is also saying a pivot in every column of A, where A is that standard matrix of T. So everything is just kind of wrapping back into itself. This is how linear algebra goes. It's like every time you define a new concept, all the other concepts just pile onto it. The other one is about spanning. If T is an onto mapping, then the columns of the standard matrix of A span Rm, but this just means there's a pivot in every row of A. So we'll look into what does it mean for a mapping to be one-to-one? What does it mean for it to be onto? That'll be this problem. We'll have some clever theorems that just says, look at the pivots of the standard matrix. So that's a special role it takes. And there's some optional reading way down below here. If you're really curious on why we care about linear transformations, we want transformations that are operation preserving in this way, that are also one-to-one and onto. If we can find such a transformation, we'll call them an isomorphism. We'll talk a little bit more about what isomorphisms does for us in algebra when we close out this section next time on Tuesday's class. But if you want to read ahead, there's some interesting algebra and some interesting drama in the world of mathematics about almost 100 years ago, or excuse me, almost 200 years ago, that has isomorphisms at its center role. So we'll start off really just by doing one of these again, finding that this transformation is linear by studying its standard matrix. It's as if the linear transformations and the standard matrix are really the two key things you need to learn about the moment you know your transformation is linear. And it goes from those two vector spaces. But any last questions at all, folks, before we call it a day? Okay, so this is the overview of what we'll be getting into. After we finish this section, we'll be moving through chapter 2. It's a short chapter. We'll just cover 3 sections. Then into chapter 3 is another short one, and we'll be into chapter 4, where it'll feel like we're redoing all of chapter 1, but slightly more abstract vector spaces for domain and codomain here. But have a great afternoon, folks. We'll be back into this next time. Yeah, absolutely. I'd be happy to do so. It's a pretty fun reading, honestly. So let me put here a reminder. Post counter example. Yeah, I'll post it, not example. I'll post it on the Canvas page just right under this extra example here. I'll just say interesting counter example. Yeah, good one. Thanks, you too.